Okay, so the title of our project is Using a GAN for Data Augmentation of Chest X-ray Images for Detection and Classification of COVID-19 Virus in Patients. So this project is motivated by the ongoing COVID pandemic with the aim of experimenting with computer vision techniques that can help in diagnosing COVID. The X-ray dataset that we obtained from Kaggle has a limited number of COVID X-rays. Hence, our project focuses on a technique to augment this dataset with the aim of improving the classification accuracy of a COVID detection model. So our project has two components. The GAN, which is used to generate new images to augment the existing COVID X-ray dataset, and we have the CNN, which is used to help classify whether a patient X-ray has COVID or not. So for the design of our GAN, we want to learn the distribution of the input chest X-ray training data, which will in turn help us to generate new COVID and normal X-ray images. We design a conditional GAN for the purpose of image generation. The conditional GAN takes in labels and noise as inputs and outputs an image based on the input label. So this slide contains the generator architecture on the left and the discriminator architecture on the right. More detailed information about the GAN architecture has been included in our paper. For the GAN training, we use a total of 7232 images with 3616 COVID images and 3616 normal images. We train the discriminator one step for every 10 steps that we train the generator. The discriminator uses the binary cross entropy loss function to discriminate between real and fake images. In the following slides, we discuss 3 experimental runs while training our GAN. For the first run, we use the original 300 by 300 image size, the stochastic gradient descent optimizer with the following parameters, and we set the mini batch size to 4. In this run, our GAN diverges because the discriminator learns too fast. These are the images generated by the GAN in the first run. We can see that the generator is somewhat attempting to learn the distribution of the chest and the lung. In the second run, we downsample the images by 2. We reduce the SGD learning rate to 0.001, and we reduce the number of filters in successive layers in the generator network. Again, this GAN diverges because the discriminator learns too fast. For the third run, we keep all of the modifications made in run 2. We change the optimizer to Adam, and we add a learning rate scheduler with the restart rate equal to 10 epochs. Again, for this run, the GAN does not converge. These are the images generated in the third run. We can see that the artifacts like lungs look more defined. This slide contains the smooth loss plots for the second run. The discriminator loss is shown in the left, and the right figure contains a generator loss. In the discriminator plot, we can see that at epoch 540, which is this gray line, the discriminator learns faster than the generator, such that the discriminator loss converges to 0, while the corresponding generator loss increases. Some of the results and observations of the GAN is that firstly, we observed improvement in the performance with each successive run. Secondly, none of the runs resulted in the GAN converging. Thirdly, blocky artifacts in the images from the first 2 runs resolved by changing to the Adam optimizer with a smaller learning rate. We tried to increase the learning step rate of the discriminator. However, this resulted in the discriminator converging too early, thereby giving poor results. Upon decreasing the learning step rate of the discriminator, we found that the generator would not learn any specialized features. In the end, we had to settle at a discriminator learning step of 10 because that gave the best performance. Now for the design of the CNN, we experimented with 3 pre-trained models, which is the Inception V3, ResNet 50, and VGG16. We removed the original fully connected layers and augmented with custom fully connected layers for the classification task at hand. We also froze the layers of the pre-trained models. Finally, the data was split in a 60% train, a 20% validation, and a 20% test split. And the data has perfect class balance, and each set has the equal number of COVID and normal examples. So this slide shows the CNN architecture, where the first block contains the pre-trained models. Then the extracted features are flattened and passed to a fully connected block which outputs the classification at the end. This slide shows the performance of the three models on the original dataset. As we can see, the VGG16 model shows the best performance. Next, this slide shows the performance of the three models on the data augmented dataset. As we can see, the best model is again VGG16 with a higher accuracy when compared to its performance on the original dataset. In fact, both VGG16 and Inception V3 have shown improvements in performance. However, the performance of ResNet 50 has gone down marginally. In conclusion, we found that training the conditional GAN was a difficult task because of the multitude of hyperparameters involved, which influence whether the generator and the discriminator are able to learn from each other or not. Although the GAN did not produce good quality images, it did seem that it was able to encode some meaningful data because we observed improved performance on 2 out of the 3 models after augmenting them with the GAN generated data. Our best model is the GAN data augmented BGG16, which produced a test set accuracy of 0.9675. Thank you.